we will start a discussion of semiconductors, one of the most important class of materials in solids, which have a wide range of technological applications. In fact, progress in semiconductor technology has revolutionized the area of modern electronics. Semiconductors are materials which have electrical conductivities, as is obvious from the name, lying between the electrical conductivity of a good conductor like a metal and a perfect insulator. So, conductivity, electrical conductivity between that of metals and insulators. For example, we have given in table form the conductivities of good conductors such as copper, gold and silver, insulators like ebonite, glass and mica, and semiconductors. The standard semiconductors are silicon, germanium and gallium arsenide. The electrical conductivity values at 0 degree Celsius or 273 Kelvin is given in the last column, and it is clear that the conductors have conductivity values which are very high compared to those of semiconductors, which in turn are very high compared to those of insulators. So, the electrical conductivity spans something like some 18-19 orders of magnitude among common materials. So, this is a very remarkable variation. That is the first feature. The second feature is that you have a temperature dependence of the electrical conductivity or resistance. We all know that in the case of a metal, the electrical resistance versus temperature is linear and then becomes non-linear and become, this is for a metal. So, it has a linear variation and then the resistivity decreases with temperature. As the temperature is decreased, the resistivity decreases. So, you see that the resistivity increases and therefore, the conductivity decreases, the electrical conductivity decreases. With increase in temperature for a metal. So, they are said to have the resistivity increases, whereas in the case of a semiconductor, conductivity increases with increasing temperature, unlike whereas a semiconductor conductivity increases. So, this is called a positive temperature coefficient. So, this has a positive temperature coefficient. Of resistance. So, this is known as PTC, whereas the metals it is known as NTC, it has a negative temperature coefficient. So, this is another important difference between the behavior, the temperature variation of the conductivity of a semiconductor versus that of a metal. Now, what are semiconductors? The typical semiconductors elements are, as I already mentioned, silicon and germanium. Both these elements belong to the group 4 of the periodic table. Another important element which is in the group 4 is carbon. So, carbon, silicon, germanium have identical electronic configurations, and this is the reason why all of them behave like semiconductors. For example, silicon has an atomic number 14, therefore, it has an electronic configuration in which there are core electrons with outermost 3s2 core plus 3s2 and 3p2 electrons. Germanium has an atomic number of 32. Germanium has an atomic number of 32, and that has an electron configuration which is 4s2 and 4p2. The essential thing is, this is the 3s and 3p shell, this is the 4s and 4p shell, but both in both cases the s and p, outermost s and p shells are occupied by 2 electrons each. So, that is why the electron configurations are similar. So, that is why they have similar physical and chemical properties. They have indeed similar crystal structure. In fact, it is also similar to that of carbon, but in its form as diamond. So, this crystal structure is that of diamond, which is nothing but carbon. So, the diamond has a cubic crystal structure. So, this diamond structure is shown in a picture. So, figure shows the unit cell of silicon and germanium crystal. In this, we will discuss this in great detail, but this is the main feature. Each atom of silicon is tetrahedrally coordinated. You have a cube, and each atom of silicon is tetrahedrally coordinated to 4 near neighbors. Tetrahedral coordination. Tetrahedron means the number of near neighbors is 4. So, each silicon is coordinated to 4 near neighbor silicons. So, there are tetrahedral bonds which are shown by shaded portions. So, the structure is basically a face centered cubic, FCC. What does it mean? That means that there are atoms not only here, but also at the face centers, and it is these atoms which are tetrahedrally coordinated. So, the basis is a simple cubic lattice with 2 molecules in the unit cell, one here and another at 1/4, 1/4, 1/4. These are the two atoms which form the basis. So, this is what gives you the tetrahedral coordination. So, the tetrahedral means the angle is 109 degrees 46 minutes. So, these bonds are shown. Basically, what is happening is that you have two electrons here, one of these electrons get promoted. In the molecular orbital picture of the bond formation, you have one 4s2 electron excited into p orbital, and then you have one electron here 4s1, and then you have 3 electrons and forming an sp3 hybridization. That is, this electron which is excited joins with these, and you have this electron with 3 electrons in the p shell, including the 1 electron which is excited into the p shell, and you have the remaining electron and 3 p electrons combined together to form sp3 hybridized molecular orbitals. And these are the ones which form covalent bonds, which are shown by the shaded region in the figure. This is also the case with most compound semiconductors. The compound semiconductors are formed by combining a group 3 element with a group 5 element, or a group 2 element with a group 6 element. So, both are compound semiconductors. The table shows these. So, you have group 2 elements and group 3 elements and group 5 elements, giving you things like gallium antimonide, indium antimonide, and so on, indium phosphide, gallium arsenide, things like that. So, these are all 3,5 compounds. In the other case 2,6 compounds, it is materials like cadmium selenide, cadmium telluride, and so on, zinc sulphide, usually sulfur, selenium, tellurium form the 6th group. So, cadmium, zinc, etc. are in the 2nd group. So, forming compounds of this kind. So, these are the 2,6 compound semiconductors. These also have similar crystal structures. You also have glasses, the compound semiconductors prepared in glassy form. Chalcogens, the sulfur, selenium, tellurium are known as chalcogens, and therefore, these are known also as chalcogenide glasses. So, prepared in glassy form, they are the class called the semiconducting glasses. They have also acquired a lot of technological importance. So, that is regarding the basic structure and basic chemistry, chemical nature of these various kinds of semiconductors. Now, we also have 2 important classes of semiconductors. There are, one is known as an intrinsic semiconductor, the second class is extrinsic or doped semiconductors. Because we have seen from our discussion of the energy band structure that the band structure, the electronic structure, consists of an occupied valence band and an unoccupied conduction band, and the energy gap is rather low. It is of the order of 1 electron volt, say. So, the energy gap is such that it is sufficiently small for carriers to be, as already discussed, carriers can be excited across this energy gap even thermally by at sufficiently high temperatures, for example, room temperature and above. The carriers can be excited thermally, some of the carriers. So, the intrinsic conductivity depends on the thermal activation of these carriers across the energy gap. So, then there is an electron excited into the empty conduction band and a hole left behind in the valence band. Both the electron and the hole move in opposite directions, producing conduction. So, you have an electronic conduction and a hole conduction in a semiconductor. This is another major difference. So, you have electronic and hole conduction. How do we know this? We know this by performing Hall effect measurements. This is why in an intrinsic semiconductor the conduction is produced thermally or by natural means automatically without doing anything, by just thermal activation. Whereas, in the case of an extrinsic semiconductor, the electrical properties are controlled by adding impurities in extremely small concentrations. So, you call that doping, controlled impurities in an extremely pure material. Specific impurities are added. We will discuss this later in detail. In order to understand what happens, let us look at the intrinsic semiconductor at a finite temperature which is above 0 Kelvin. Let us look at a particular site where there are, see, all the bonds here are shown by 2 dashes, 2 lines, and this means the number of bonds. The number of lines is equal to the number of bonds. Now, suppose we consider an electron, yes, that is marked E. Now, because this electron has been lost by the atom A, and therefore, you have only one line. So, you have what is shown here is just the tetrahedral arrangement in 3 dimensions is projected onto 2 dimensions. So, the 4 tetrahedral bonds are shown schematically in this manner. At 0 Kelvin, all the atoms are well linked with a perfect covalent bond, and there are no free electrons, there is no conduction. The semiconductor is a perfect insulator. But as the temperature is increased, the thermal energy will cause the atoms to migrate. Once the electron gains enough thermal energy, it gets dislodged from this bond. So, the dislodged electron is now free to move in the crystal lattice, and this electron will now respond to an electric field, thus contributing to the electrical conductivity. Now, in this figure, the dislodged electron was shown by the letter E. So, the bond AB has lost one electron. So, it has only a single link. So, between A and B there is a missing link or a missing electron. A missing electron is shown as a hole H, by the letter H. The electron is by the letter E in the figure, while H is for hole. So, when the electric field is applied, the electron moves in the direction opposite to that of the applied field, while the hole moves in the opposite direction. Now, the missing link in the bond AB may be restored if it captures another electron from a neighboring bond, and then the hole moves on to that new site. So, this creates a hole now if it moves between C and D rather than from A and B, because AB has captured an electron. So, the hole moves in a direction opposite to that of the electron. It is along the direction of the field. So, both electrons and holes contribute to the conductivity. The free electrons and the holes are considered as defects in an otherwise perfect covalent bonded structure. So, in an intrinsic semiconductor, the number of holes and the number of electrons are equal. This is an important concept. Whereas, in the case of an extrinsic semiconductor, as we already saw, we have to add impurities or dope it with impurities. Now, the impurities can be of two types. The impurities which are added can be either donor impurities or acceptor impurities. A donor impurity is one which donates an electron. For example, an element from group 5 in the periodic table. We already saw these elements like phosphorus, arsenic, antimony. Whereas, acceptor impurities are one which are from an element from group 3. Such as bismuth, aluminum, indium. So, these are added in extremely small quantities in at the parts per million. If it is a donor impurity, you add an electron, so it is said to give n type conductivity, because it is electronic conduction. Since the charge on the electron is negative, it is called n type semiconductors. When you dope a pure material, semiconductor silicon or germanium, with a controlled amount of donor impurities from group 5 of the periodic table, for example, you result in an n type semiconductor. Whereas, if you have an acceptor, this will give me p type semiconductor, because it accepts an electron and thus creates a hole. So, the conduction is by an excess of holes, and the hole has a positive charge. It moves in the direction opposite to that of the electron in an electric field. So, this is usually from these. So, therefore, you have n type semiconductors and p type semiconductor. So, in an n type semiconductor, in addition to the electrons and holes which are created intrinsically by, say, thermal activation, there are additional electrons which are donated by the impurity atoms. And so, the number of electrons exceeds the number of holes. Here Ne, the electron concentration, is greater than NH, the hole concentration. So, electrons are known as the majority carriers. whereas in a p type semiconductor the number of holes exceeds the number of electrons, and therefore holes are the majority carriers. Therefore, holes in an n type material are also known as minority carriers. Similarly, here the electrons are minority carriers. Each impurity atom creates a hole in the case of a p type semiconductor, and the holes move in the direction of an applied field, contributing to a hole conduction. So, the number of holes exceeds that of electrons. The amount of donor or acceptor impurities usually added is extremely small, 10 to 100 parts per ppm, parts per million. So, that is the usual concentration. In order to do this, it is very important that we have an extremely pure basic host crystal material, silicon or germanium, to which a controlled amount is added. So, this is very important, and that is why the production of semiconductors is an extremely difficult operation involving very important techniques of crystal growth, such as the Zosheralski technique, zone refining, and so on. We will not go into these technical aspects. So, the crystal growth, crystallization of these pure semiconductors is a technology by itself. Now, if we want to understand the nature of conduction in a quantitative manner, we have to discuss it in terms of, for an intrinsic semiconductor, we go by carrier concentration. How to determine the carrier concentration? In an intrinsic semiconductor, in order to know this, we have to know the number of electrons and holes. So, for this we have to go back to the so called electron density of states. So, in order to find the concentration of carriers, we have to go to the number density of states, n of E dE, which is 4 pi times 2m by h cross square to the power 3 by 2 times E minus E c to the power half. This is because in the band structure of a semiconductor, this is taken of the bottom of the conduction band is taken as E c, and the energy is measured from this. So, that is why the energy term becomes E minus E c. In addition, we have the Fermi Dirac distribution function, which is 1 by exponential E minus E f by kBt plus 1, but at high temperatures when the temperature is sufficiently high that E minus E f by kBt, the exponential is large compared to this, we can forget about this, and this can be written as e to the power minus E minus E f by kBt. Combining these two expressions, we get the expression for the number of electrons in an energy interval E to E plus dE, and if I integrate it from E c to infinity, that will give the number of electrons. So, if we carry out the integration we arrive at the result 2 pi m k b t by h cross square to the power 3 by 2 into 2 exponential E f minus E c by k b. That will be the carrier concentration. Here of course, we do not write m as the mass of the free electron, since this electron is in the periodic potential, we replace it by the m star, the effective mass, and we denote this as the effective mass of the electron by writing m e star. Similarly, we can calculate the hole concentration, where we have to write instead of f of e should be replaced by 1 minus f of e, because this depends on the probability of a state E not occupied or unoccupied. When it is empty, then the electron get into it, and therefore this depends on the number of vacancies. So it will be 1 minus f of e, and that again gives you 1 minus 1 by and that will give you e to the power e minus E f by k b t. So this should be used in order to find the whole concentration, and we integrate from the minus infinity to the top of the valence band, because that is where the holes exist. So this is from minus infinity to the top of the valence band E v. So n h is integral and that gives me the result m h star k b t by h cross square to the power 3 by 2 into e to the power E v minus E f by k b t. So the number of holes and the number of electrons, whenever a hole is created here, an electron gets excited automatically. So the number of holes and the number of electrons are equal in an intrinsic semiconductor. Therefore, NH times Ne is what I call Ni square, the intrinsic carrier concentration. So that from this relation we can find the intrinsic carrier concentration as, with a bit of algebra, this can be shown to be and what is Ec minus Ev? That is nothing but the energy gap. So this becomes just exponential minus Eg by kBt, 2 kBt, because we are taking the square root here. So we can see that the conductivity, which is proportional to the carrier concentration, intrinsic carrier concentration, will depend exponentially on the argument Eg by 2 kBt. So, if the energy gap, which is usually of the order of 1 electron volt, that is the energy gap. So, and the temperature is 300 K, this will be the sort of, this leads to the known exponential dependence as well as the known positive temperature coefficient of a semiconductor. Inverting this, we can also find the Fermi energy. It turns out that the Fermi energy is 3/4 kBt log mh star by me star to the plus Ec plus Ev. If the hole and electron has the same effective mass, then this term will become 0, leaving only this, and this will be Eg by 2, the average of Ec and Ev. So, the Fermi energy lies midway between the conduction band and the valence band. In a semiconductor. So, the intrinsic carrier concentration goes the exponential minus Eg by 2 kBt, this temperature dependent exponential term. The table shows the variation, the temperature dependence of this factor. So, the intrinsic electrical conductivity will consist of two terms, one involving the electron and another involving hole. Well, we can similarly discuss the concentration of majority carriers in an extrinsic semiconductor. We will do that next time.